that a condition variable has a type, let's say it's a struct CV, right? And it has two functions, wait and notify. Wait takes two arguments, struct CV star and struct lock star, right? And notify takes one argument, that's struct CV star. The idea is that you would use the condition variable to check, to wait on a condition, and somebody will notify you when that condition becomes true, right? So this is used to wait on a condition to become true, and this is used to wake up or notify any thread which is waiting on the condition, right, to become true. Right? Should usually be called when the condition becomes true. Right? So, in general, the way you are going to use wait and notify is something like this. You're going to say if some condition, right, and you're going to say if not some condition, let's say the condition is not true, then you're going to wait on the condition variable, corresponding condition variable. This is the corresponding condition variable, convar, and notice that there is a race condition between the check and the act of going to wait. So typically, you will want to have a lock to make these two things atomic. So you're going to have some lock. So you're going to say acquire, some lock, and the second argument of this wait will be that lock. Right? So typically, this is how you are going to use wait and wait. Right? And of course, here you're going to release the lock. And you may want to do other things here. Right? So this is typically how it is used, except that if there are multiple threads that could be waiting here, if is not enough, you may want to recheck the condition after you come out of wait, right? Because if there are multiple threads that are waiting, it's not necessary that when you come out of wait the condition is still true. So you should recheck the condition, and so instead of if, typically you would replace it with a while. Right? So this is a very common pattern in which you use condition variables. Of course, so this is to wait, and then similarly there will be another thread which will say notify on convar. Right? Now clearly if some thread is calling notify, that condition should have become true, right? So before this there should be some code which makes the condition true. And after the condition has been made true, the thread is allowed to call notify. Typically the thread should call notify only after the condition has been made true. Right? Also, once again, there can be a race condition between this and this, and so you typically use a lock, and so you could say acquire lock, right? and release lock, right? The effect of notify is that it wakes up all the threads that are currently waiting on convar, right? And when the threads wake up, the first thing they're going to try to do is to try to acquire the lock. One of them will get the lock and will proceed. The other will get the lock later and it will proceed later. It's possible when the second thread proceeds, it again checks the condition and the condition becomes false because the first thread has already sort of made the condition false, right? Now there was a question last time, can I swap notify and release? Right? So what can happen if you swap notify and release, which means you release the lock before you call notify. It's not usually recommended that you do it, right? Although even if you do it, it's possible that your code is still correct. So we saw one problem last time called lost notify, right? And we solved this problem using locks. So let's say this is a problem and this is the solution, right? Similarly, there's another problem which can be called spurious notify. Spurious notify basically means that it's possible that no thread is waiting and you still call or the condition is not true and you call notify, right? So what can happen is if there's a race condition between the condition becoming true and the call to notify, then between these two, if another thread gets to run, then it can make the condition false. And then you call notify, then you are calling notify even though the condition is false, right? So that's the problem of spurious notify. Spurious notify is not a correctness problem, it's okay. I mean, you call notify. If you are writing your code in this way, where you are enclosing the wait with a while, then even if you do notify, the thread is going to come out of wait and it's going to again check the condition. Most likely it will again go back to wait. So spurious notify causes unnecessary wake-ups. Right? And if you don't put a lock after notify and you put a lock before notify, then or you release the lock before notify, then you can have more spurious notifies because what will happen is that you have released the lock and the condition may now become false and now you notify and you may be just waking up threads unnecessarily, right? So it's okay. So I mean to reduce spurious notifies, it's better that you release the lock after notify. Okay. All right. So let's just rewrite our producer consumer example once more. So basically we had void produce a char data, and I just say if head plus 1, or let me just let me just say if q is full, right, whatever it means to check whether the queue is full. So if queue is full, then wait on not full, right? And also because you want to make sure that there are no race conditions, you will first do acquire queue lock, right? You will acquire queue lock, then you will wait not full and you will release the queue lock, and you will do this in an atomic fashion using this wait interface, right? And then you will and you'll make sure that, so wait will also reacquire the queue lock after it comes. Also you will replace this with a while, right? Then you would produce an element, right? Then you may want to notify any consumer on not empty, right? And then you will release the lock. Okay. Similarly, if I look at consume, let's say char consume void, you will acquire Q lock. You will say while Q is empty, wait on not empty and release the Q lock. And also reacquire it when you wake up. Right? That's what it means. And then consume an element. At this point, you can be sure that the queue is not empty, right? Because you've taken a lock and you have checked the condition and the queue is definitely not empty here. So you can consume an element. And then you will say notify not full. And then you will release the lock. Right? Notice that I'm, in this code, I'm just simplifying things. I'm always notifying. And so this can result in spurious notifies. So, I could also say if Q became, if Q was full, only then call notify. Right? Similarly here I could have said if Q was empty, only then call notify. Right? Okay. All right. So that's a producer consumer example using locks and condition variables. If there are any questions, please feel free to interrupt me at this point. Okay. Moreover, this example works even if there are multiple producers and multiple consumers, right? So even if there are multiple producers, only one of them will be able to get the lock, Q lock, and then it will produce or it will either wait. It's possible that multiple producers start waiting. So let's say there are 100 producers, all 100 find the queue to be full, all 100 will go to sleep, right? They will start waiting, they'll go to sleep. Then one consumer wakes up. So let's say one consumer gets to run and the consumer consumes one element, queue becomes not full, so it calls signal. The effect of signal is it wakes up all the processes that were waiting. So all 100 processes wake up. The first thing all the 100 processes will try to do is that they will try to acquire this Q lock. Obviously all 100 cannot get the Q lock simultaneously, so only one of them will be able to get the Q lock. Other 99 will have to wait. The one which gets the Q lock will first check the condition again, and it will find that the queue is not full this time, right? Because the consumer has just consumed one element, so the queue is not full, and so it will produce one element. But now once it has produced an element, the queue again becomes full. Now all the other 99 producers will also acquire the lock one by one, but each only to check that that the queue is full, and they will go back to sleep again. So what will happen is if there were 100 producers sleeping and one consumer consumes one element, it will wake up all the 100 producers. Only one of them will be able to produce anything. Other 99 will again go back to sleep, right? Because they will check and the condition will be false. Okay. All right. Okay. So now I'm going to discuss another synchronization abstraction. So we have seen two synchronization abstractions. First we saw locks, and locks were being used for mutual exclusion. So we saw locks, and locks were being used for mutual exclusion. All right. Then we saw condition variables. And condition variables were being used for waiting on a condition to become true. Right? Now I'm going to discuss another synchronization primitive called semaphores. Right? And semaphores are basically typically used for counting. Right? So before I explain how what semaphores are, let's just understand. No, so before I discuss how semaphores are used, let's first understand what is the abstraction of a semaphore. All right. So semaphores. Once again, semaphore has a type struct sema. Let's say, right? Just like there was a struct log, there was a struct CV. Now there is a struct sema. Right? Just basically a type. It's a stateful type, which basically says. You know, it represents or stores the current state of the semaphore. And there are two functions in the semaphore. One is called P, struct sema star, right? And another is called V. Okay, all right. So what do these P and V mean? All right. Okay. Just pull out the page where I have things. All right. So P and V, and there's also another function called init. And the init function basically initializes a semaphore to an integer value, int value, right? Okay. Now let's understand what do these functions mean. So I've told you that there's something called a semaphore, and the semaphore has some state inside this type called struct sema. It gives you three functions: p, v, and init, right? So first let's talk about the init function. Init function simply, so the semaphore has a state, an integer state. Okay, and so what does init do? Init simply copies the value of val into sema, right? So basically, you know, it initializes the counter of sema to this value val, right? That's what init does. It basically uses the argument val and initializes the semaphore with the value of val. All right. What does p do? P is you can think of it as a decrement operation. Right. So P basically decrements the value of the semaphore by 1. Right. So decrement by 1. Or in other words, minus minus. Right. So when you call P on the semaphore, it basically decrements the value of the semaphore by 1. All right. Similarly, what is V? V is increment by 1. Or in other words, plus plus. Right. So V basically increments the value of the semaphore by 1. Right. So the semaphore has an integer value. P will decrement the value by 1 and V will increment the value by 1. Okay. So this sounds very simple, except that there's one more thing, right? The thing is that the semaphore value has to be always greater than equal to 0, right? So it has to be a non-negative integer. All right. So if ever the value, you know, somebody calls P on a semaphore whose value is already 0, and so you cannot decrement it anymore, it will wait, right? So the semantics are that P is going to wait for the semaphore to become become 1. So it's basically going to wait for the semaphore. So if you call P on a semaphore whose value is 0, then the thread will have to wait. And for how long will it wait? It will wait till somebody calls a V on the semaphore or increments the semaphore to, let's say, 1 or 2 or whatever, and so now I can decrement it and then I will fall through. Okay. So decrement by 1, but also wait if sema dot count is equal to 0, right? So don't decrement if it is 0. If it is 0, wait for it to become non-zero or positive, right? And if it is positive, then just decrement it. All right, so that's the semantics of a semaphore. Also, these functions are atomic. So this operation of decrementing and this operation of incrementing are atomic operations. Also, the operation of going to wait is atomic with respect to other operations on the semaphore, right? So if I were to write what the semaphore means, basically let's say if I want to implement a semaphore, let's say implementing example implementation. Example implementation is, for init, I will just say, so firstly let me just define what my struct sema is. So let's say struct sema has a count, which is an integer. Okay. Then I have a function called init, right? And init is going to do what? So it takes an argument sema, it takes two arguments, sema and val, and it basically says sema pointer dot count is equal to val, right? So recall this is the signature of the init function. It takes two arguments, a semaphore and a value, and this is its semantics. It just says sema dot count is equal to value. All right. Let's see what is P. So P is the decrement operation, right? And it's going to say if sema dot count is equal to 0, wait. All right. And then here it will say sema, otherwise sema dot count minus minus. Okay. Also notice that this whole thing is atomic. Okay. Here this wait is not the condition, is not the same as the wait and the condition variable. I'm just using wait to say sleep, or I could have said sleep. Okay. And this whole thing is atomic. Right. And let's write V. And V basically does what? Sema dot count plus plus. It just increments the count. All right. But it also basically does what? It wakes up any sleepers. All right. So if there are any sleepers that are waiting, then you will wake up, and this whole operation is also atomic. So what will happen? Let's say if a thread calls P on a semaphore that is the value 0, then it will go to sleep. Then another thread comes along and calls V. It will increment the semaphore and will call wake sleepers. This thread will wake up, and then it can decrement it now. Right? So the invariant is that sema dot count is always greater than equal to 0. Right? What does an invariant mean? A condition that is always true. So always sema.count will be greater than or equal to 0. Also, yeah, so that's basically the invariant. Okay. Also notice that I use an if here, but depending on how my wake up sleepers works, I may want to say while here also. So if there are multiple people who are sleeping, then and all of them, let's say, wake up, then they should again check the condition, right? And you should also have a log something. So I'm not basically describing how it's made atomic. You could implement this using, you could implement semaphores using locks and condition variables. It's very easy. You basically within the semaphore you basically define a condition variable and a lock, and in P you acquire the lock and check the condition, and then if the condition is if the semaphores.count is equal to 0, then you wait and you release the lock, right? So let's say if I were to implement semaphores using locks and condition variables, right? So here's one way. I could define struct sema, right, and have two fields. So I'll have the field called count as before, but I'll also have two fields and two other fields called struct lock and struct CV, right? So let's say I have a struct sema and I have defined it like this, and how will I implement init? So init sema is nothing but you will first acquire what? Sema.lock, right? And set sema.count. So init sema.val. So sema.count is equal to val, and you will release sema.lock. Okay, init is very simple. Let's see how will you implement P. So if you want to implement P on sema, you could say acquire sema.lock, right? And now you are going to say while sema.count is equal to what? 0. Then wait on what? On sema.cv and release sema.lock, right? And then you could say sema.count minus minus. You can be sure that at this point sema.count is greater than 0, right? Because if it was equal to 0, you would have spun in this loop. Now if you have come out of the loop, you are sure that sema.count is equal to 0 and you are holding the lock, right? So you're going to say release sema.lock. Okay. And how will you implement V? Well, V is simple. Just say sema. V on sema is basically nothing but, once again, the first thing you need to do is acquire the lock. All right. And then you say sema dot count plus plus. Notice that here I don't need to wait. I can, I'm just incrementing it. And so if when I'm incrementing it, I cannot make it 0 or less than 0. So there's no problem with that. All right. And then I say what? Do I just release the lock? Or maybe I should call notify, right? So I say notify, or I can say if sema.count is equal to 1, which means it has just transitioned from 0 to 1, then it's possible that there are some people who are sleeping, right? Some threads which are waiting on the CV. So I'll say if sema.count is equal to 1, then notify sema dot CV, right? And then I'll say release sema dot lock. Okay. So basically I've used locks and condition variables that we now understand to implement the semantics of semaphores, right? So there are three functions in it. You basically take the lock, initialize it, release the lock. T, which is decrement operation, you take the lock, check if it is equal to 0. If it is equal to 0, go to wait, right? And keep waiting till it is equal to 0. So you put a while loop there and you go to wait. If you come out of the while loop, it basically means it's greater than 0. And then, so you can decrement it and you can release the lock. And V is going to increment it. It's going to acquire the lock, increment it, check if it has just become 1, which means there may be somebody who is sleeping on it. So you notify the condition variable. Anybody who is sleeping on the condition variable, notify it. And so everybody wakes up and you're going to again check and then you release the lock, right? Okay. So if there are any questions at this point, please feel free to ask me. So there's a question from VCE where the question is the count the number of resources? Yes, I mean, so so how am I going to use the semaphore? I'm going to discuss very soon. Let's just understand what a semaphore means first, right? So I'm just telling you what a semaphore means. How am I going to use it? I'm going to discuss it very soon, right? So let's hold on that discussion for some time. How am I going to use it? Let's hold on. But let's first understand what a semaphore is. What does a semaphore mean? A semaphore means a semaphore is a stateful type called struct sema. It has three functions, P, V, and init, right? And the semantics I have told you already. So let's just understand those semantics. And also let's understand how you can implement these semantics using locks and condition variables, right? There's another question from VCE where they ask you, so there's a question that can we use condition variables for increment? No, condition variables can only be used for wait notify, right? Condition variables have no state. They don't have any state. Semaphores have state. Semaphores have a state because they have this value of count, right? That's a state. Condition variable has no state. You are either waiting or you are, somebody is notifying on that condition variable. There is no state in the condition variable. Do locks have a state? Right. So I'm saying semaphores have state, right? Because they have this count variable. Condition variables have no state, right? Because it just notifies anybody who is currently waiting. It doesn't matter, what was the value of the condition variable. Condition variable has no value really. You're just saying wait and notify, right? And those two basically meet. So if there was a notify and somebody was waiting, then the wait comes out. That's all. There's no state. Semaphores have a state because there's some current value of a semaphore. It's either the initial value, or depending on how many times P has been called, it will be decremented, or how many times V has been called, it will be incremented. So semaphore has a state. Now my question to you is, do locks have state? Right? So I would want somebody to answer this. Do locks have state? Okay, LNMIT says yes, the locks have state. Recall that the locks have, or it's not acquired, right? So you cannot call acquire twice. That's because the lock has a state. The state could be a 1-bit state, which basically indicates whether it's locked or whether it's unlocked, right? So a lock has a state of 1 bit. A semaphore has a state of 1 integer. right? A condition variable has no state. All right. Okay. All right. So now let's understand how these semaphores are used. So I've explained what are semaphores, but let's understand uses of semaphores. So the first example I'm going to take, so let me say example uses of semaphores. Right? And the first example I'm going to take is the same example that we have been studying so far, that's the producer consumer example. Okay. So I had a producer and I had a consumer, and basically I showed you some code earlier which was using locks and condition variables to basically synchronize between the producer and consumers. But I can do the same thing in a much simpler way using semaphores. All right, and let me show how. All right. So let's say once again I have a queue and a head and a tail, and apart from that, let me now I'm not going to use locks or I'm not going to use condition variables. I'm going to use semaphores to do synchronization. All right. So let me have two semaphores. Struct sema. One semaphore is basically how many characters I have in the queue. So let's say chars. So let's say n chars. All right. And another semaphore is basically how many empty slots I have in the queue. So let me call that n holes. Right. So a queue has some number of characters and some number of holes. Right. So let's say the queue is initially of size max. Right. So what I'm going to do is I'm basically going to say init n chars to 0. Initially the queue has no characters. So n chars is going to count the number of characters in the queue. Okay. So n chars is just going to count the number of valid characters in the queue. Alright. And n holes is going to count the number of empty slots in the queue. Alright. So also I'm going to initialize n holes to what? To max. Right. So initially n chars will be 0 and n holes will be max. Right. And now I'm going to use these two semaphores, n chars and n holes, to do my producer consumer example. Right. So here's how producer consumer works. Let's say this is produce. So void produce C. I'm going to say I'm just going to say P on n holes. I want to decrement the holes by 1. Right. Produce an element. Right. And then say V on n chars. This produce an element is nothing but, incrementing head by 1. That's all. We have seen this before, right? So produce an element we understand. Similarly, consume is nothing but the opposite. You decrement chars, consume an element, and then increment holes. Right? That's it. That's your producer consumer using semaphores. Right? Let's see what's happening. Initially n holes is equal to 0 or n holes is equal to max, right? So initially n holes was equal to max and n chars was equal to 0. So initially if there was a consumer thread that comes in, it will call P n chars is 0, so it will keep waiting here. Right? It will keep waiting here. if somebody produces something, he will produce an element and then he'll call v nchars, and so when it calls v nchars, this one will come out of its loop and it will start consuming an element, right? So n holes and n chars are going to do the synchronization between the producer and the consumer, right? Notice that this code looks much simpler than the code that we had earlier, where we were using locks and condition variables. Basically what has happened is all the logic of the locks and the condition variables is now subsumed by this one function called p, right, on both sides. So all that while loop with a wait inside it is all within the p now, right? And similarly the signal or notify is within the v, right? And so it makes it easy to handle such programs where you can basically where you need to basically count resources. So here you are counting resources, right? You have a queue has n slots, so each slot can be considered as a resource, right? So initially there are n holes, so there are two types of resources. One resource is the number of characters and another resource is the number of holes, right? And so basically you use p to consume a resource and you use v to produce a resource, right? So you're basically counting resources using p and v, right? This code works if there's only one producer and one consumer, but if there are multiple producers and multiple consumers, then you may want this producing an element may require may have race conditions, so you may also want to have another lock here. So you can say acquire lock and release lock. So you can make this operation of production of an element atomic or mutually exclusive, right? Similarly you can say acquire lock and release lock. This is just for mutual exclusion, right? This is not for your producer consumer synchronization. This is for multiple producers, multiple consumers. If there's only one producer and one consumer, there's no you can do it without even having a lock actually, right? But it's always safer to have a lock. So because when you're going to produce an element, you're going to be accessing a shared structure called Q, you're going to access shared variables called head and tail, so you may want to acquire a lock before you do all that. Okay. All right, so any questions at this point? So how am I using the semaphore? I'm basically initializing. So let's say I have some resources and I want some kind of counting behavior on these resources, right? Basically, there are people who want to access these resources. These resources could be elements in a queue, for example, right? And so you basically have threads that are coming in and trying to access these resources, and you want to make sure that those resources are counted properly. One way to do that is to do this manually or yourself by maintaining a count variable and using locks and condition variables to make sure they are properly synchronized. A simpler way is to just use semaphores, right? Semaphores internally will be doing the same thing, right? But you can, your code becomes much simpler. Okay. In this case, I had a queue and I had a producer and consumer, and I'm using semaphores to basically guard access to my queue. Another example is, let's say you have some resources, right? So you have, let's say, 100 threads. Let's say 100 threads, right? Accessing, let's say, 10 printers, right? Let me draw printers as these boxes. Okay, so you have 100 threads accessing 10 printers, and you want to make sure that only 10 threads are active at any time, right? So all these threads want to print something, and all these threads want to print something, but you want to make sure that only 10 threads are active any time, right? Because if there's an 11th thread that's active, then there's a problem. Right? Only 10 printers can, there are only 10 printers, only 10 threads could be printing anything at that time, right? So one way to do it is basically have a semaphore called n printers. So you basically declare a semaphore, struct sema n printers, and you initialize it to 10. Right? And in the code of these threads, you're going to say P. So let's say the thread code, you're going to say P on n printers. You're going to do, execute the print command. And then after you're done executing the print command, you may say now I have released the printer, right? So you may want to say V on n printers. Right? And that's it. Right? So basically, if there are 100 threads that come in, only 10 threads will be able to go here. Other 90 threads will keep waiting here. Now, as and when the threads come to complete, they will call V, and so more threads will start falling through from here. Right? Okay. So you can use semaphores for counting resources like this. Okay. Let's also see how semaphores can be used to implement anything else, right? So for example, even locks can be implemented using semaphores. How will you implement locks using semaphores? Well, very simple. You just use a semaphore, let's say struct sema. Let me call it sema lock. A lock that's implemented using semaphore. And if for acquire, if wherever I want to acquire a lock, so I can say acquire is nothing but P. So firstly, I'm going to initialize sema lock. So I'm going to say init sema lock to 1. Right? So lock is nothing but, lock can be thought of as a resource which has only one instance, right? So just like I had 10 printers, a lock is a variable which has only one instance, and so only one thread can get it at any time, right? So just like I said, there can only be 10 threads that could be printing at simultaneously. Similarly, there can be only one thread that could be inside the critical section, right? So I could use the semaphores to implement locks. I could just say init sema lock 1, right? And so now acquire will basically mean P on sema lock, and release will basically mean V on sema lock. That's it. Acquire is P, release is V, assuming that the sema lock has been initialized to value 1. Right? So semaphores can be used to implement locks. All right. What is the other thing the semaphore can be used for? So any questions at this point? I'm actually, maybe I'm going a little fast. I don't know if people are following this. All right. So I can use semaphores for scheduling. Okay. So how? Let's see. Let's say I want to compute. There are there's thread 1 computes X, right? Then it computes Y, all right? And let's say there's a thread 2 that computes Z, which computes it over F. It's a function over X and Y. Sorry. And then let's say there's another thread called T3 that just prints Z. Okay. Now let's say I want that this statement should only be called after this statement has been called and this statement has been called. Right? Similarly, I want that this statement should only be called after this statement has been called, right? I only want to print a valid value of Z. So I need some kind of synchronization. I'm basically saying that this statement should execute only after this has been executed and this has been executed. So I need a dependency edge from here and a dependency edge from here. And similarly, this one should happen only after this. Right? So how does one do this? Okay, so one way is to use semaphores. How will you use semaphores? Okay, let's say you could declare 3 semaphores, Vx. So let's say struct sema. Let's say struct sema. Let's say I declare 3 semas, Sx, Sy, and Sz. Okay, and let's say I initialize all of them to 0. So init Sx to 0, init Sy to 0, init Sz to 0, right? So notice that this time I'm initializing the semaphore to 0 and not to a positive number, right? In the lock I initialize it to 1, in the case of printers I initialize it to 10. In the case of a producer consumer queue I initialized 1 to 0 and another to max, right? So but here I'm initializing all of them to 0, and now what I'm going to do is I'm going to call I'm going to write code like this. I'm going to say T1 is going to do what? It's going to compute X, and after it has computed X, it can call V on Sx. Basically signaling that X has been computed. Alright, so it basically increments Sx by 1. Then it computes Y is equal to something, and then it can signal that Y has been computed by calling VSY. Alright. Now thread T2 can say I want to wait for Sx to become, for X to become computed. So one way to say that I want to wait for X to get computed, you call P on Sx. Alright. Similarly, you call P on Sy. You want to wait for both of them to get computed. Alright. And then you compute Z. Now Z has been computed, so you may want to say V on Sz. So now Z has been computed, right? So I'm basically using the semaphore to indicate whether the value has been computed or not. If it has not, if it has been computed, its count will be equal to 1. If it has not been computed, its count will be equal to 0. And initially nothing has been computed, so everything's count is 0, right? And so finally T3 code could look something like this. I just say I wait for Z to get computed, and then I call print Z. Right. So what you have done, using this code you have ensured that this statement can only execute after this statement. Similarly, you have ensured that this statement can only execute after this statement. So basically you have ensured that this dependency graph is followed using semaphores. So this is scheduling with semaphores. Okay. All right. So let's so I'm done with the material for today, but let's interact with the students a little bit. So let me ask you this question: have you? So I had suggested last time that you implement a producer consumer queue for yourself, right? So I would highly recommend that all the students implement a producer consumer queue using pthreads. So right, so use pthreads. Pthreads has all these functions. So pthreads also has pthread lock. So pthreads basically allow you to do pthread create, that creates a p thread. That's similar to the thread fork that we have been talking about. It has p thread mutex lock. These are just lock acquires and lock release. And pthread library also has condition variables. Pthread cond wait and pthread cond signal. Right. So these are your these are basically your condition variables. Wait and notify. Right. These are locks, acquire, release. So I would highly encourage you to implement a producer consumer queue using pthreads. Right, you have all the you have a lock, you have condition variables. So you should implement a producer consumer queue using pthreads. Then you should implement producer consumer queue using semaphores. All right. So implement, use a different pen. Have it. So here are my suggested exercises. Implement producer consumer using locks and CVs, right? Then implement semaphores using locks and CVs. Then implement producer consumer using semaphores. All right. Finally, I have also shared a hare and turtle assignment. I have shared it with the local instructors who sent me an email. So I would highly recommend that you do the hare and turtle assignment using threads. Right? So earlier I had asked you to do the hare and turtle assignment using processes and pipes, right? So now using threads. And when you're using threads, you're free to use locks, condition variables, and semaphores. Okay. So I highly recommend that you do these exercises. It will greatly improve your understanding of how things work in practice. Okay. Are there any questions? Okay, if there are no questions, let's stop. Okay, good. And let's meet next Monday.